Hi friends, welcome to my YouTube channel. In the previous video we discussed about how to derive a vertical stress equation depending upon the Bosnian influencing factor, and with this coefficient we have derived some equation for the vertical stress because of the point load. And in this video I told you we'll discuss about the important points regarding this applications, limitations, and example on this. Okay, if you haven't watched that video, please go and check it out in my channel, as that is the important part, like prerequisite to watch this video. Okay, in that we have derived some Bosnian influence coefficient through which we'll be getting the vertical stress. Okay, so we have some standard values of IB depending upon the R by Z values. Okay, so first we have to calculate R by Z, and from this table we can just take the value of IB, which we can substitute in this equation, that is IB multiplied by Q by Z square. Okay, Q by Z square. In this equation we have just taken Q by Z square as outside constant and outside part, and whole term remaining this remaining of this Q by Z square as IB. So whenever we are taking R by Z square, that is R by Z is constant over here, the IB will also be constant, that will not vary. Okay, so here is the table of that values. This is the R by Z value, and corresponding to that whatever the IB values, the Bosnian influencing coefficient are mentioned over here. See, this is one table, this is the other, and this is the other and other. Okay, so depending upon the R by Z values, we are getting the IB value in this table. Okay, coming to the important points that I told you we'll discuss in this video are as follows. The vertical stress does not depend upon the modulus of elasticity and the Poisson's ratio. The solution has been derived assuming the soil is linearly elastic. That is, whatever the elastic modulus of elasticity is there, we are taking it as constant. Also the Poisson's ratio is constant. That is, the material is linearly elastic. So depending upon this assumption, we can say that it does not depend upon the E and nu value, the Poisson's ratio and modulus of elasticity. It is independent of those values. Okay, the intensity of vertical stress just below the point load is given by this value. See, this is the IB value. I told you sigma Z is nothing but IB multiplied by Q by Z square, where IB is this. Okay, when we are constraining the values of R by Z, we will directly get the IB value from the table I showed you before. Okay, I have shown you that in the previous part of this video. At the surface, Z is equals to 0. Okay, in R by Z, this Z is equals to 0. The vertical stress just below the load is theoretically infinite. However, in actual case, the soil under the load yields due to very high stresses. See, in the theoretical part, that is when we are deriving, when we substitute Z is equals to 0 means the value we'll get is infinity. But in actual conditions, that is in practical conditions, the load, see, whenever a load is acting, the stresses will be more at this point. That is, at Z is equals to 0, the stresses are maximum in practical conditions. Whereas in theoretical conditions, when Z is 0, it is infinity. Okay, next, the vertical stress sigma Z decreases rapidly with increase in R by Z ratio. At R by Z is 5 or more, the vertical stress extremely becomes small and is negligible, which can be observed from the table 1. See, I will be showing it over here. See, whenever the R by Z is varying, I told you this is R by Z ratios, and we'll get the corresponding IB values. So here whenever the R by Z is 5, it is very negligible, 0.0001, and at 10 it is almost 0. Okay, so whenever the R by Z value is 5 or more, the vertical stress extremely becomes small and is negligible, that is almost equal to 0. See, sigma Z is nothing but IB into Q by Z. Here the square is to only to the Z. Okay, so Q by Z square. Here whenever I am saying R by Z, in IB is nothing but the ratio of R by Z, right? it is varying in it is dependent of r by z. So whenever the r by z value is increasing, ib value will decrease. Whenever ib is decreasing, stresses will decrease. Okay, I will explain you in this formula. See, in this ib, r by z is nothing but the denominator value. Whenever the denominator is increasing, the ib value will decrease. If it is increasing, it will decrease. And from this equation, whenever the ib is decreasing, the stresses will decrease. Okay, so that is the relation of r by z and the sigma z. Okay, whenever the r by z is increasing, sigma z will decrease. At phi, it is negligible. At phi or more, actually the foundation loads are not applied directly on the surface of the ground. Bossinet's solution can be applied conservatively to field problems concerning to shallow foundations, provided the distance z is measured from the point of application of load. See, we know that actually the loads are not applied directly on the surface of ground, but we take the basic assumption as the load is applied directly on the ground. So it is only generally it is applicable to the shallow foundations with the z measured from the point of application of load. Okay, we also discussed this in the derivation part, that is in the part 1 video. If you haven't watched that video, please go check it out, and please do subscribe to my channel, that would greatly help me. Okay, going to the next point. Especially at shallow foundations, the Bossinet's solution gives conservative values and can be safely applied in engineering problems. So the main applicability of this is shallow foundations. As the soil is not fully elastic, the stresses determined are not approximate. Okay, they are more or less same as the exact value. And coming to the limitations part, the solutions are basically obtained for determination of stresses in purely elastic bodies and gradually applied to soils also. Even though soils are not purely elastic, experience indicates that the results obtained are satisfactory. Okay, the basic assumption we took was the material is homogeneous, isotropic, and also elastic. Okay, but in practical conditions we don't see elastic soils, right? But I can say the values obtained are satisfactory. And for practical cases, the Bossinet's solution can be safely adopted, particularly for homogeneous deposits of soil, man-made deposits, and limited thickness of sand deposits. Whatever the naturally made deposits are there, they might be heterogeneous. That is, no material will not be same throughout the medium. Okay, that is only applicable to the homogeneous member. Next, coming to the third point, one more limitation is the point loads applied below the ground surface cause somewhat smaller stresses than are caused by surface loads, and Bossinet's solution is not strictly applicable. However, the solution is frequently used for shallow foundations and where z is measured below the base of the foundations. Okay, this is the same as the previous point we have discussed. The point loads applied below the ground surface cause somewhat smaller stresses, but we know the Bossinet's solution is only for the maximum loads and for the shallow foundations where it is not applicable. So that is the another limitation of this. Coming to the application of this, I'm also explaining how to solve a problem on this in this application itself. So application of Bossinet's equation on horizontal and vertical planes. The vertical stress distribution on a horizontal plane. Coming to the horizontal plane, we are just evaluating how the stress because of this applied load Q is varying. See, sigma z is equals to IB into Q by z square. We know this value. If z is 2 meters, see, whenever we are taking in a horizontal member the variation of the stress, the z is constant, the depth is constant, right? The z is constant in IB value, the z is constant. Okay, we'll get this IB as like this value. See, z square, z is 2 square is 4, right? So 1 by 4 is 0.25, 0.25 IB into Q. So the value of sigma z can be computed from various values IB and for different values R by z. See, IB is nothing but 3 by 2 pi 1 by 1 plus R by z whole square to the power of 5 by 2. Here is the value. So how to calculate this variation? I'll show you that example also. Here in the horizontal plane, z is constant, z is 2 meters. So first of all, we'll write R values, that is the distance of this member see this medium, we are considering this stress at this point. The horizontal distance, whatever it is there from the applied load, is r. The vertical distance is z, that is constant. So the r values are written, r by z values are written. We know the ib values when r by z is there. Okay, from r by z we can evaluate ib values from the table I have shown, and from that we can simply substitute in this sigma z value. We'll get this equation. Okay, so this is how we'll calculate the vertical stress distribution on a horizontal plane. When I am talking about the vertical stress distribution on a vertical plane, the vertical stress distribution, that is load developed due to the stress developed due to the vertical load, that is Q. Here the R is constant. See, R is constant. The horizontal distance is constant. Through this we are taking the variation. The Z is varying over here. Okay, in this case the radial distance R is constant and the depth Z changes. For the values of different R by Z, we can evaluate the values of IB, right, from this equation, and simply substitute in the sigma Z value. Okay, so the major vertical stress occurs at the depth of Z is equals to 1.22 meters. From this table, I will show you the table. So here I have written the values of Z that are varying. R is constant 1 meter. Okay, and we'll evaluate R by Z values from which we can get IB value. Again we'll substitute this in sigma Z. We'll get the vertical stress distribution on the vertical plane. Okay, remember in vertical plane the horizontal distance or the radial distance R is constant, whereas in horizontal plane the depth Z is constant. Okay, yes, that is it for this video guys. Please like, share, comment to my channel. Please subscribe to my channel, that would greatly help me. I appreciate you watching this video. Thank you.